Hello, today I'll be discussing our research into demand-side management of the electrical grid. So as renewable generation sources that are intermittent, like solar and wind, increase, utilities are looking at innovative ways in which they can balance the demand and supply on the electric grid. Here I have given you an example of a situation in which PV generation is in excess in the middle of the day, which would typically require the curtailment of traditional generation sources like coal or gas-fired power plants. Then it's followed by a peak demand period in the evening in which there's no PV generation present, in which case we would have to have a rapid ramp up in those traditional generation resources, which is often much more inefficient than if you were to operate them at constant load. So to smooth this demand curve, we're looking at new ways at which we could manage the demand side of the energy equation. So one way that we're doing this is looking at behind the meter load shifting for residential customers. So houses in the United States consume about 55% of the total energy consumed by buildings, and within those houses, half that energy is consumed by an HVAC system, another 20% by the water heater. So we can use this HVAC water heating devices as a form of virtual battery. For example, with the HVAC system in summer, we might use it to pre-cool the house below the typical set point by a couple degrees during the midday period when we have that excess PV generation, which would allow us to shift energy out of the peak demand period by reducing the HVAC electrical demand at that time. Because each of these houses is contributing a very small amount of energy to the load shifting, it's desirable to aggregate them at a regional level. So one way that we're looking at assessing this regional potential is through load disaggregation of the advanced metering infrastructure smart meter data to look at each of the individual electrical components in the house and then use them for forecasting. So we take the main signal and apply a non-intrusive load monitoring or NILM algorithm to that signal to disaggregate it into each of the individual appliance components, then take that electrical data along with local weather data and combine those into a forecast in which we can look at the amount of electrical demand that we're expecting to be present during a given demand response event. Once we do that, we can assess our total capability for demand response. That would be our maximum amount. And future research might be looking at actually installing some devices within the home for control response using these appliances, or additional sensors to gather more local data that would improve our forecasts, further facilitating demand response in the residential setting.